the truss members, that will be directed tension will be there. Then bridge components, that will be subjected to direct tension. Then cables, that will be subjected to direct tension. So in this case, so the tensile strength is the very important or the most important property that we have to determine. Along with that, the properties, the parameter like modulus of elasticity, etc., is very important, that should be determined. Then in addition to that, we are using the steel as reinforcements in cement concrete. So if we are thinking of a beam, when it is subjected to lateral loads, it will be transverse loading, it will be bending. So the bottom is subjected to tension and the top is supposed to be undergo compression. So for taking the tension, we are using this steel rods. So the in that way also, the determination of tensile strength is important. So now we are using different terms in this. So the stress, when we say the stress in this tensile test, it is the linear stress that we are determining or the normal stress that we are determining, usually represented by the letter sigma. That is equal to the term is the resistance against the externally applied load. That is the stress, that's per unit area. The resistance per unit area against the applied load is called the stress. And the equation or how we can determine is, that is the applied load divided by area of cross section. That is in general stress. Then strain means the change in the dimension divided by original dimension. Here, change in length delta divided by original length L, that is strain. Now, modulus of elasticity, Hooke's law states that within elastic limit, the stress is proportional to strain, and the ratio of normal stress to normal strain is known as modulus of elasticity, which can be written as stress by strain. As per the notations that we are using, P represents the tensile force that we are applying, A, the area of cross section of the steel specimen that we are determining, we are using for the test, delta is the increase in the length, and capital is the length of the original length of the specimen. So stress by strain, P divided by A is the stress and the delta by L is the strain. So when we are writing P by A divided by delta by L, which can be rewritten as PL divided by A delta. That is the equation that we are using for determining the modulus of elasticity. Then there are different. So we have in general seen what is meant by stress. While conducting the test, there are different important points that we have to note during the time of loading. In the tension test, we are increasing the load from 0 to a maximum value. Then within that limit, so there are certain things or points that we have to note. So the first point is the yield stress, so that we can explain by using this figure. So this is the load versus elongation curve that we are plotting after conducting the test. So this is the typical this is the load elongation curve. So in general, we can plot stress strain curve also. It will be having almost the same shape. Okay, so it will be the same shape. So we have seen the different points here represented by 1, 2, 3, etc. So the section 1, 0 to that point represents the limit of proportionality, within which when we apply the load, the strain will be proportional to stress. That area is called that particular duration of loading is called the limit of proportionality. Then 2 is the limit of elasticity. That means that is called the elastic limit. Within elastic limit, we know that we are applying a load. Then when we remove the load, the specimen will come to its original length. That is called the elastic limit. Beyond which, if we increase the load, so there will be some permanent deformation that will be existing. Okay, that is not elastic. So that is the elastic limit. Then there are 2 points marked as 3 and 4, the upper yield point and lower yield point. So the yield point means during this loading, momentarily the specimen loses its strength. That means, so till now we are increasing the load, the deformation is also increasing. And at certain point, even without increasing the load, this load is remaining the same, but the deformation increases. So that is called the yield points. Where it starts, it calls the upper yield point, and where it ends, that is called the lower yield point. So within this limit, the material has got some loss of strength, but it regains its strength and continue to deform as the load increases. Okay, so beyond that, then it comes to a maximum value. The load will come to a maximum value, then decreases, then the specimen breaks. So this is the case of a typical elastic material in which we have the specific ultimate point and also the breaking point. That means this is because the specimen is getting elongated, its area of cross section reduces, and gradually it loses its strength and it breaks. So this is typical in the case of a ductile material, whereas in the case of a brittle material, so there is no specific breaking and ultimate point. It will be the same. That means the load increases, the elongation increases, and percentage elongation is taking place less in the case of a brittle material. That means all of a sudden it breaks. No specific 5 and 6 points that will be coinciding. So we will have a simple curve without this yield point, then upper limit, lower limit, etc. So it will be initially straight, then a curved curve. So then it stops there. So that is with respect to a brittle material. So this is with respect to the standard curve for the elastic material. Now coming to the different terms. Yield stress means, so where the yielding take place, that particular load divided by the original area of cross section, that is called the yield stress. That means the stress means force divided by area. So when we take force as the yield load, then it is called the yield stress. Then ultimate stress means what is the stress, maximum stress the specimen can sustain. That is called the ultimate value, that is equal to the maximum load at the point of this 5 divided by its original area of cross section. That is called the ultimate load. Then breaking load means, so sixth point. So here we see 6. 5, the value of 6 will be less than that at 5. That is the breaking load divided by, there are two stresses that we mentioned. One is the nominal breaking stress and the other one is the actual breaking stress. The nominal breaking stress means the breaking load divided by its original area of cross section. That means we are not considering the reduction in the area. But when we consider the reduced area of cross section, it is called the actual breaking stress. So these are the parameters that we are determining after conducting the tension test. Now we shall go for the instrument by which we are conducting the test. So this is conducted in a machine called a universal testing machine. So because this name is because, so this machine is not only used for conducting the tension test, it can be used for conducting the compression test, shear test, bending test. Different types of tests can be conducted on this machine. So it is called a universal testing machine. It has got two parts. So in the figure, the right one is called the control unit and the left portion is called the so this portion is called the loading unit, where we can keep the specimen and apply the loading. This is a typical photograph taken from the net. So this is the actual machine that is available in our laboratory. So here the left unit is called the control unit, almost similar to whatever we have seen, but this loading unit is different. So there are different arrangements here in our machine. So this bottom portion, so this is used for holding the specimen in the case of a tension test. Then this is stationary. Then this middle part, that is a movable part, and the upper jaw is there, which is also stationary. So we can move this middle portion up and down depending upon whether we are conducting the compression test, tension test, etc. In the tension test, we are keeping the specimen here at the bottom, then clip it here, so properly hold it here, then it is connected to the middle part, then raise the middle part. Then what will happen is the pulling effect will be there on the specimen. So increase the loading from 0 by operating this control valve. The machine is operated by hydraulic pressure. That means a fluid, oil is present and that will be pumped in order to apply the loading. So during the oil pumping, gradually the load will be increased from 0 to a maximum value. We can measure the load using this dial gauge. Now this machine has got different ranges. We say range of the machine. Depending upon what is the type of the specimen that we are testing, we have to set. So in order to adapt, require only a small load or very small load to break. Then if we go for a higher range, then we cannot read the load etc properly. That means it will break all of us as with a small load. So in order to enhance or facilitate the reading of the loads and also applying of the load to the required level, we are setting the machine which is called selecting the range. Accordingly, we have to keep the dials. So these dials will have different dimensioning depending upon the range that we are taking. So the machine has, so this is the come to the calculation here. So this is the control unit which two valves operating this valve. So the valve is first of all open, both the valves are open. Then so operate the machine and some initial should be there. The valve is open and then adjust to the valve. So this dial is used for taking the load. Okay. So we are taking two dimensions. One is two measurements we are taking. One is the load and the other one is the elongation. Elongation is measured by a dial gauge which is known as an extensometer. Okay. So using this dial we can measure the load. So at every increase of, so if we use it as say 0, 10, 20, that we have to that depends upon what is the range of the machine or what is the expected ultimate load of the specimen. Okay, so accordingly we will keep the dial and or at constant intervals we are taking what is the elongation, the load and its corresponding elongation. That is a measurement that we are taking. So here it shows the loading panel more clear. So this is the test specimen that we are using, a circular mild steel specimen we are using as the test specimen. So the procedure is, first of all, we have to measure the diameter of the specimen at three different points and take the average value of the diameter of the specimen. Then the specimen diameter is taken with the help of a vernier calipers. In the case of a specimen of considerable diameter, otherwise we can use a screw gauge. Usually we measure it using a vernier calipers. So use the vernier calipers, measure the diameter at three different points and take the average value, use it as D. Then calculate the initial area of cross section A0 using the equation pi d square by 4. So that is the initial area of cross section. Now we have to set the machine to the required range. So range calculation. For that, we have, depending upon what is the specimen that we are using, that means if it is a mild steel rod, we usually assume that the ultimate strength of the material is 500 kg per centimeter square. That is the assumption that we are making. And using this one, we can find out what is the maximum expected load that will require for breaking of the specimen. So that is equal to the expected stress into area of cross section. So we know what is the value of A0. Assumed strength is 5000 kg per centimeter square. Now what is the relationship between stress and the strength? So we have seen yield stress, ultimate stress, breaking stress, etc. So what is the maximum stress the specimen can sustain? That is called the strength of the material. Okay. So here ultimate strength means the maximum stress or the maximum ultimate load divided by area of cross section. That is the strength. That we are assuming it as 5000 kg per centimeter square. So the load, the expected maximum load is equal to the initial area of cross section into 5000. So much kg will be the ultimate expected load. This is the expectation. Okay, accordingly, we have to set the machine. The machine has got three ranges. Our machine, it is 0 to 3 ton. That means this calculation we have made, and here we are getting that it is some 2,300 kilogram. We are getting as the expected maximum load, that is below 3 ton. The 2,300 means 2.3 ton, which is less than 3 ton. Okay, then we have to set the machine at the in the range 0 to 3 ton. So that range is set using this counterweight and this arm available on behind the machine. Okay, so the range will be written there, so we can set the machine accordingly. Okay, so there will be different loads available. We can use this counterweight for setting the machine. Then, so these things we can you can directly see when you visit the lab. Then the second range is 0 to 10 ton. That means when we calculate the maximum load, if we get a value beyond 3 ton, that means we are getting some 4.2 ton, 4,200 kg, then we have to set the machine within the range 0 to 10 ton. Okay. Similarly, if it is beyond 10 ton, that means we are getting some 12 ton, 15 ton, or even 20 ton, then we can set it within the range of 0 to 30 ton. So accordingly, we have to use the, so if it is used for this 0 to 30 ton, we have to use a counterweight also. Then the load applied will be according to this range. Accordingly, we have to change the dial. Now see here in the graduations, there are graduations available according to the range. So it will be for the 0 to 30 ton, it will be 0, starting from 0, and will be 30,000 kg will be the maximum value. So we can take 10, 20. So it may be some 2, 4, like that. Accordingly, the graduation will vary. So we can take the measurements accordingly. Now machine is set, then we have to make some certain markings on the specimen. So we know that when the specimen is pulled, it will be getting elongated and break. So the studies or the research have been made on this reproducibility and the reliability of the test. It is found that when we use this or take the elongation of a particular distance, then it is found to be more reliable. That means consistent. When we do the experiment different times, it remains the same. That is called the consistency. Consistency is observed when we adopt a particular gauge length. So the gauge length that we are adopting suggested is as per the IS specification. The gauge length that we have to use is 5.65 root A0. That means on the specimen, this is the specimen. So first of all, you mark the center of the specimen. Then on either side, you have to mark the certain length. That length is 5.65 root A0 divided by, so mark your center. So assume this value 5.65 root A0. If the specimen has got a diameter of around 10 mm, we will get this value as some 5 centimeter, 5.65 root A0. Okay. Now mark the center first. Then on either side, you mark 2.5 centimeter. That means the total gauge length is 5 centimeter. Then similarly, you mark the next point, so that in between, when the specimen is breaking, it will be breaking between two punch marks. So the initial distance between the punch mark was say 5 centimeter. Now we can measure, you join the two broken pieces and measure what is the final length. Then for that 5 centimeter, what is the actual elongation that has been taken place. So we can get accurately what is the percentage elongation. Okay, for that we have to use this gauge length. So mark the center line. So mark this 5.65 root A0 throughout the length of the specimen. Okay. Now we have to fix an extensometer on this. So this is the one type of extensometer. This is not exactly what we are using, but for your awareness, I am saying. So this is the extensometer that we are fitting. This extensometer will have two legs that will be fitted on the steel rod at the two punch marks, sharp punch marks that we are making, so that there will be proper gripping of the extensometer. And we are measuring what is the within the proportional limit. We are taking the extensometer reading in order to calculate the modulus of elasticity. Then the extensometer that is there in our lab now has got the gauge length of 5 centimeters. So there should be two sharp punching in order to fit the extensometer. And what extension is taking place for that particular length that we are measuring using this dial gauge. So it will show its least count. It will maybe say 0.02 centimeter or millimeter. So there are extensometers with the different least counts. We have to note down what is the least count of the extensometer. Then only we can complete the calculation. And also this rod that is shown is not the type of the rod that we are testing. So this is the standard type of the specimen that is tested in the UTM. So we are using the actual mild steel specimen. Okay. So after the test, there will be some reduction in the area of cross section that is taking place for this standard specimen. So this reduction is called the necking. So the shape of the necking will be at one edge there will be a convexity, and at one edge after the breaking there will be a concavity. That is called a cup and cone. So that is the normal way in which a ductile material will be sealing. Now load fit the specimen. See, so this is the way in which the specimen is fitted in the loading unit. So on the lower part, hold it by means of the clamp, then connect to the next top portion, other end to the middle jaw also. Now operate the machine, apply the load, then the middle portion will move up, pulling the specimen. Now you note down what is the load at the regular intervals. Then what is the corresponding elongation? You measure from the extensometer, then enter into the tabular sheet. So this is the schematic diagram of the specimen within the loading jaw. So this is the tabular column in which we are entering the readings. So load at here it is marked as 200, 400 kg, 600 kg, 800 kg, 1000 kg. So that can be read from the dial, loading dial directly. Okay. So this dial has got a two needles. It is shown as one red needle. One is a dummy needle, because after increase in the loading, that means it will go on increasing the loading. At the yield point, there will be a momentary stationary for the needle will become momentarily stationary, then continue. So that point we can directly note down. Then it will continue and become a maximum value. Then it will be reduced, because there the reduction.
Hello, ma'am. Hello. Is there an issue, students?
In the area of cross section is taken. Are you audible?
Yeah, for some seconds it was missing, 30 seconds around.
The
Can continue from this slide, I think.
Okay.
This slide you can continue.
Okay.
From the beginning.
Okay. So then we can note down what is the maximum value using the dummy needle, then the breaking value where the actual black needle will stop, that is the breaking point. These values we can note down. Then we can note down the elongation. So this extensometer will not be kept for the entire duration, because the specimen is going to break. Before that we will remove. So the value of extension and the corresponding load is required for calculating the modulus of elasticity. That is required only up to the proportional limit. So beyond that, we will remove the extensometer, then allow the specimen to fail. We will take the maximum load as well as the breaking load. Okay. So these are the measurements that we are taking, and will this So this is the way in which we are noting down the load 200, 400. So at regular intervals we are taking here the maximum load that is
Hello, ma'am.
taken and the
Hello, ma'am. Your
hello.
presentation is gone. PPT is not visible now.
Okay, okay, okay. So the load and the corresponding extensometer reading. So this extensometer reading will be in terms of number of divisions on the. We multiply with the least count and we will get the extension in millimeter or centimeter depending upon the least count that we are using. Now we have to plot the graph with the load on the y-axis and the elongation on the x-axis. And from this, we can determine what is the value of modulus of elasticity. So the equation used is PL divided by A delta, where P is the load, then L is the length or gauge length, and A is the area of cross section, initial area of cross section we are using, and change in the length. In order to calculate this one, after plotting this one, see here, after plotting, we are giving a best fit line. That means so all the points may not be passing through this straight line. So we cannot draw a straight. So we are assuming that we have taken the reading within the proportional limit. So not the assumption, but we are doing that also. Proportional limit. And so the graph between load and elongation or stress strain, that should be straight. Okay, so we have to fit a best fit straight line. So that will not accommodate all the points. So what we can do is either we can draw by using the maximum number of points, or to the given points you fit an average line. So that is the load elongation curve. So from that you can, so here not necessary to come to the origin. So in one way we get maximum points, you can draw it, because 0 is 1 point. Just as simple, we have many other points also. From this, you take one intercept. It's y coordinate and the x coordinate you take. So this we can use in the equation. So this y intercept will be the p value. Then this x-intercept will be the corresponding delta value. Then what is L? L is the extensometer gauge length. So for in our case, it is the 5 centimeter. Okay. Then A is the A0, original area of cross. Using this, we can determine the modulus of elasticity. Similarly, we can determine the other parameters. Yield point load we have noted down, divided by area of cross section. Original area of cross section will give you the yield strength or the yield stress. Then ultimate maximum load also we have noted down. So that divided by original area of cross section will give you area of cross section will give you breaking divided by the reduced area of cross section. So after the test, so we have to take two measurements. One is what is the increase in the length. That means join the two pieces together, then measure the distance between the gauge point that we have marked already for fitting the extensometer. Okay, so that will be more than 5 centimeter. Then you keep the specimen together, pieces together, and find out the reduced area of cross section. That means reduced diameter we can measure and use that for getting the reduced diameter. Reduce the area of cross section that you use in calculating the actual breaking stress. And you have to calculate the percentage elongation. The percentage elongation is the final length. That means which is more than 5 centimeter minus the initial length. In our case will be 5 centimeter divided by the initial length into 100. That means this will be a percentage. Similarly, reduction in the area of cross section. That is A0, initial area of cross section, minus the final area of cross section divided by A0 into 100. That is the percentage reduction in the area of cross section. And these values, this percentage elongation is specified for a mild steel specimen. the modulus of elasticity shall be in the within the range 2 into 10 raised to. So we are getting in kg per centimeter square, that you can convert into Newton per mm square. That will be the standard unit now. So 2 into 10 raised to 5 to 2.1 into 10 raised to 5 Newton per mm square. That is a standard value. Similarly, the more than a good elastic material. If it is less than that, means it is not so elastic. So that's all about the presentation. Now we shall see a video. So this is exactly not exactly the machine that we are using. This is almost in the similar way that we are using. Is the video visible?
Now, this
Yes,
is the
ma'am, it's
typical
visible.
stress strain curve for the mild state. The OA is the linear portion and whose
So
slope
these
will give
things
us
I
the
have already
modulus of
explained.
elasticity.
I will go to the way in which the specimen is marked, etc. Very slow.
F is the breaking stress. Now to start the vernier calipers.
Kind of diameter using your calipers.
So from that we will get the area by using the formula pi by 4 d square, and we assume an approximate ultimate stress of 600 megapascal.
So instead of 5,000, they have assumed 6,000 kg per centimeter square or 600 MPa as the
By
ultimate
multiplying
stress.
with this ultimate stress, we will get the expected ultimate load. So usually our expected ultimate load falls in the range 0 to 120. So which can be selected using the range selector. Now behind this machine we have to put counterweights corresponding to this range. So here we are having A is equal to 60 kilonewton and A plus B equal to 120 kilonewton. So for the range 0 to 120, we have to put both this A and B.
So this is different for our machine. Our machine is a 30-ton UTM. So this load range that they are discussing may be different.
We have to mark the gauge length in this road. So gauge length is calculated using the formula L naught is equal to 5.65 root A naught. So suppose we are getting gauge length, then first we have to measure the total span of the road, mark its midpoint, now from the midpoint, on either side of the midpoint, we have to take half the gauge length. Now from this point onwards, we have to take the whole gauge length and mark it across, completely across the road. Make sure that you put the 10 centimeter in excess here, because when we are fixing, it should be convenient. We have to punch it using the punch. The point should be punched, and then we have to keep it in the machine. So first we have to tie
The fixing is
top
different.
crosset.
Here,
So fix a
the
crosset.
machine
These
is
are both the crosset, the middle crosset, which can be adjusted using this.
here the specimen is fitted between the top and the middle one. So for this machine, the flexure arrangement is at the lower portion. That is why it is fitted there. So for our machine, the flexure arrangement is at the middle, and the tension portion is the top, and the compression at the top. Sorry, tension at the bottom, and the compression is set at the top. So this is a reverse. No problem.
In the road, we can now fix the extensometer. The elongation readings are taken for 2 kilonewton interval.
Now,
After taking the sufficient readings, we have to remove the extensometer.
see here also the extensometer is also slightly different. This has got two dial gauges, and they will take both the readings and take the average. For our case, we have only one dial gauge, so there is no need of taking the average. That is the difference. So now it is loading. See that's at every significant points they will note down the load and the corresponding elongation.
The point to the next stationary, and that point is called the end point. After that,
Here it has come to
the ultimate load, where the road breaks.
see here one needle is
Out from the machine and observe the neck to be a cup and cone shape. Now find out the neck diameter using the vernier calipers. We'll get the load corresponding to the extensometer reading, and the actual extensometer can be found out by multiplying the divisions into least count. Now coming to the stress can be obtained by force by area, and strain is dealt by LE, where LE is the extensometer, that limb length or the gauge length. That here we are taking it as 10 centimeter. Now from that we can plot a straight line graph whose slope will give us the modulus of elasticity.
so here in this they are plotting the stress strain curve. So in our case we are plotting the load elongation curve. So from this itself we can get the value of P and delta, as I have already explained, and get the value of modulus of elasticity. Okay. Now the readings for which you have to do the calculation is also, I will show that also. So that will be uploaded to the classroom, and you can complete the calculation. Don't know. So it is available here. Whatever given is, I will tell you. You have given with what is the load. The tabular column I have already shown you. Know in that the load and its corresponding extensometer reading is given to you. I don't know why I cannot project it. Okay. So the load and the corresponding extensometer reading has given to you. The least count is mentioned here. So the last column, extension in mm, that is to be obtained by multiplying this extensometer least count. So for the first column, 9 is the extensometer reading and the extension will be 0.002 into 9. Similarly, 11 into portion you have completed. Now you have given with the different load values. The yield point load is 3150 kg, ultimate load 3300 kg, braking load is 2300 kg. Now these values can be utilized for yield stress, ultimate stress, the nominal braking stress and the ultimate braking stress respectively. Okay. Now the initial diameter. For the initial diameter, you have the main scale reading, then vernier scale reading. You have to find out what is the diameter, then average diameter you have to take. So multiply the vernier scale reading with the least count and add it to the main scale reading. That will give you the diameter. Similarly, for the reduced diameter also, least count and values have given to you. You can calculate what is the reduced diameter. So initial area of cross section, reduced area of cross section, both you can calculate. Now finally, the distance between the punch mark after braking. That means that will give you what is the total length of the distance between the punch mark after the elongation has been taken place. So that is given as 6.4 centimeter. The initial value of gauge length was 5 centimeter. So you can take the change in the length as 6.4 minus 5, that is 1.4. Divided by its original length into 100 will give you the percentage elongation. So this also will be given to you in the classroom, the PPT. And do you have this group mail? So you send me the mail ID. I will send the recorded videos. Any doubt? Jigal, have you noted down the attendance? Now it is almost 68%. The
Now
total strength
68%.
is
It's 69,
68%.
69,
So,
ma'am. It was there. I think someone log out now.
left. Okay.
Yeah.
No problem. You note down the attendance. Any doubt
Yes.
from the students? Doubt? Is 124 now. So while writing or doing the calculation, etc., if you have any doubt, you can anytime call myself, me, or Jigil sir and clarify it and submit the record. Okay. So as told, next Sunday before 9.